So last week we had started doing gravity, force, and weight, and we went through the definitions and how to distinguish between force and weight and mass. Just to recall, force is a push or a pull, and how do we find force? Force is mass by acceleration. Just to recall, force is equal to mass by acceleration. We know that mass is a measure of how much substance an object has, right? So this is a constant value, right, of a given object. Your mass does not readily change unless you would physically remove something from that object. And then we have, this pen is so small. And then we have weight. Weight is the force exerted by a body due to gravity. So you're going to take your mass and you're going to multiply it by the acceleration due to gravity. So your weight is a little different from your mass. So here, depending on where you are, what your value of G is, your weight will be different. So your weight is variable while your um, mass is constant. So you have to know how to distinguish between the two. Please don't try to make the mistake of saying something is weight when you're actually talking about mass. Just to remind you all, mass is measured in kilograms or grams, and this is for physics. Don't say you're going to go in the market and ask for 10 newtons a baji. They'll look at you like you're crazy, right? And weight is measured in newtons. So carrying on, reading from the handout, let's see. Looking at Aristotle, not Aristole. It's not English, so it's pronounced differently. So Aristotle, a renowned Greek and renowned ancient Greek philosopher, believed that force applies to a body determined its velocity. So we know that force is actually equal to mass by acceleration, but this is way back in, like 10 BC, 50 BC, very long ago. And he had come up with the idea, all right, that if you were to increase the velocity of an object, that the force will be larger. So let's see what his argument was. Now, this was way back then when they were still developing the scientific method, where they made an observation, they made a hypothesis, and then they performed an experiment to prove whether or not the hypothesis was true or not. So you always have to come up with a hypothesis first, and then you have to experiment. You just can't go and say, well, A is equal to B, and say, take my word for it. That is not how science works. We make a statement, we go and test the statement, and if the statement doesn't work out to be true, we tweak our experiment. So let's look and see what he did. Now, his arguments were based on observations rather than experiment. So he thought, which made sense, right? If you had a one horse drawn carriage back then, and one horse could obviously only move with a certain amount of velocity. So that horse was moving a certain velocity, could only pull the wagon at a certain speed. And if the wagon is moving at a certain velocity, I'm not going to draw a horse here, all right, and it's moving forward at a certain velocity, obviously it's going to exert a certain amount of force. The amount of force that we know that the wagon is going to be exerting will depend on how quickly it takes to stop the wagon. So he said, it did not take one horse to stop very quickly, right? If you had one horse, it stopped really, really quickly. He said, if you took more horses and these horses move faster and faster, it took more force to slow down the wagon, which did make sense. But he was only looking at this from observation, standing by the edge of the road, all right, looking at horses going down the whatever, going down the the alleyway or the roads and just looking at them. He wasn't really performing experiments. So let's see. The argument that he had presented were based on the fact that one, to pull a chariot at a greater speed required more horses and therefore provided greater force. Two, a moving body comes to rest when the force on it is removed. Now, we can see there are two inherent problems with these statements. One, to pull a chariot at a greater speed required more horses. The only reason why the chariot moved at greater speed with more horses is because they shared the load. If one person had to push a car, that's going to be really hard. But if 6 people stand up behind a car to push a car, it is generally easier. Right? And why did that happen? Because the load was shared. So this first point did not really work out because he did not take into consideration that each horse is now sharing the load of pulling the wagon. So if one person had to pull, say, 500 pounds, that's really heavy. It's only so much you can pull. But if 20 people had to pull 500 pounds, that's going to be easy, right? It'll be like pulling your dog down the road or getting pulled by your dog down the road. Same thing, right? So this is where that um, observation was not really correct. Second one, a moving body comes to rest when the force on it is exerted. So he looked and realized that when the horse stopped moving, the carriage eventually came to a rest. But he didn't take into consideration if a horse was really running and pulling that carriage behind it and came to a stop, what's going to happen? That carriage is going to continue moving and roll onto the horse. That's not a good thing, Olio. Not good at all. But what he didn't realize that when a driver needed to stop his carriage or his wagon, he would slow down the horse. The horse takes a while to slow down. It's like, a horse will be running really, really quickly and then stop on a dime. That's how you break horses' legs and you have to put them out. Okay, so he didn't take into consideration that the horse needed to slow down in order for the wagon to slow down. Eventually, they did build brakes for wagons, so, so they didn't damage the horses as much. There are brakes for wagons. And we noticed if I were to just move something, take a ball on a flat surface and roll it, right? I'm going to roll that ball and let it go. Will the ball stop rolling the instant I stop touching it, or is it going to continue rolling? Anybody?
When it stopped up,
Y'all do that like right now. If you take your pen and let's roll it across the table, and the
when
instant
you
you
put your
take it,
hand, it would stop.
no, if you take your ball and roll it, if you just push a ball with your hand, will it continue rolling?
Yeah, yeah.
Right?
Yeah, man.
Same
Oh, I
thing.
thought you asked if you put your hand and stop it.
No. Right?
Oh,
Same thing for a car. If a car is driving down the road and the driver takes his foot off of the accelerator, is the car going to stop driving? Going to stop moving?
No.
No, it continues moving. All right. So here, once you have the force on it removed, that is not going to stop your object. It's just going to stop your object from moving any faster. So he made some good observations, but it weren't quite true because they didn't take into consideration things like speeding up, slowing down, otherwise known as acceleration and deceleration. Now, why do we talk about acceleration and deceleration? Force is a product or a product of acceleration. An object has to be accelerated in order for a force to be applied. Now, if an object is moving at constant velocity, if your velocity is constant, will you have an acceleration? Will it be speeding up or slowing down if it is moving at constant velocity? Anybody? Saying that again. If a car or an object is moving at the same speed, constant speed, is it speeding up or is it slowing down?
It's it's going in.
It going the same speed, right? Nicholas, what are you saying?
Okay.
I'm listening.
It's going here.
Slowing down.
If a car is moving at the same speed, meaning it's driving on the highway at 60 kilometers an hour, is it speeding up or is it slowing down or is it remaining the same?
Must it remaining the same?
Remaining the same,
Oh,
constant
yeah.
velocity. Constant velocity means it's moving at the same speed. So if something is moving at the same speed, it has no acceleration. So it does not experience a force on it. Now, take this, remember this because we're going to come to that just now when we look at Newton laws. Okay, only when an object is speeding up or slowing down do we have a force being experienced by our object. Just think about that in your brain a little bit. We come into that just now. So continue reading from the handouts. But Aristotle's observation were on real life situations with friction. Friction is one of the most important mechanical force that exists. If friction is negligible, an object will accelerate when pushed along a level surface by a constant force. Meaning, if I were to push something, it's going to get faster and faster. If there is no force that results in a unique velocity for the object, and therefore Aristotle's law of motion cannot be correct. Remember, he did not take into consideration that the object was accelerating or decelerating, and force is a product of acceleration. So this is where his laws could not be worked out. So it was, wrong that he came up with a law. How the scientific method works: you all make an observation, you come up with a hypothesis, then you perform experiments, and your data from your experiments will lead you to develop either a scientific theory or a law. Now, a scientific theory is just right below a law. All right, it is different from the word when somebody says theory means to guess. No, scientific theory is basically like a smidgen just below law and fact, because it has gone through the rigorous process of experimentation and observation and then calculations and proof. So he did not perform any experiments. So he could not even say that that law would have applied because he completely disregarded the entire scientific method. So let's continue reading. Now, Aristotle was in ancient Greece. Continue reading. His theory was eventually discredited and replaced by that of Newton. So Isaac Newton, quite frankly, the top one greatest physicist of all time. Not two or three, top one. All right, greatest physicist of all time. He had looked at how objects behaved. He had looked at how motion influenced other objects. He had looked at how light changes and influences the things around them and how it can be changed. Now, he did this during a big, massive pandemic. So while he was stuck home, he was changing and rewriting the rules of physics. That stands to this day and will probably never be broken. So, Sir Isaac Newton's, let's look at this. Newton laws, reading from your handout. Sir Isaac Newton is one of the founding fathers of physics. His brilliant mind and very inquisitive brain led him to describe many aspects of mechanics and light. It is because of his work we are able to determine how to send a man into space. This was back in the 1500s. The physics that he derived, the calculations and equations he derived, is what we use to send men into space. All right, and this was back in the 1500s. It just needed technology to get there. He invented calculus, a branch of mathematics that lies as the foundation of physics. This is why I tell you all, if you want to go further up in physics, you need to be doing add maths, because all the maths, the further up you go, will be add maths and applied maths. So he invented calculus, which is the foundation of physics, engineering, and economics, etc. So we should look at the three laws of motion that he devised. Every year when they give out Nobel Prizes for economics, more than half of the time, it's not an economist that wins it, it's a mathematician that wins it. Because they came up with a new formula that can be used to describe how world economic trends change, how how patterns emerge and how they can and deviate and flourish in different situations. So calculus, without calculus, we can't do a lot of things on this planet properly. So we should look at the three laws of motion. We're going to look at very simple laws that he devised. You'll have to learn these three laws and how they apply. So Newton's first law. Let's look at the definition. A body continues in a state of rest or uniform motion in a straight line unless acted upon by an external force. Let's read that again. A body continues in a state of rest or uniform motion in a straight line unless acted upon by an external force. That sounds like a nice physics law. It sounds nice and comprehensive and sort of sciencey. Anybody wants to take a stab at this as what this means in regular English, even though none of those words are complicated? What do you think this means in regular English?
That object
Uh-huh.
will be in motion unless an external force, like,
That's the same thing. Give me an example.
oh, a, say a ball rolling on a hill. Unless
Yes.
it's by someone, it will continue rolling on the hill until it reaches a point of rest.
That's very good. Anybody else wants to give a stab at this? Give me an example that explains how Newton law, first law works. Anybody else? Let's read the law again. A body continues in a state of rest. What does rest mean? Stationary. Or in uniform motion, meaning not changing, in a straight line unless acted upon by an external force. Anybody wants to give me a simple explanation, a simple example that demonstrates this? Anyone else?
Look, if an object is at rest,
Uh-huh.
it stays at rest, or if an object is in motion, it will continue to go at a constant velocity unless it is acted upon by a force.
Give me an example that demonstrates this.
Miss, for example, the same horse and them, right? If they're going down the road and they meet up a big stone, they just stop, they just slow them down a little bit.
Yeah. Anybody else? That's okay.
Miss, if it have a football on the ground and it's
Uh-huh.
stationary and not moving,
Right.
if someone kicks it, then it will by an external the external force will be the kick and it will begin to move. So it will go from rest and to begin to move.
Very good. All right. That's really good, y'all. He just realized that something has to change its motion only when something else causes it to, and that has to be an external factor. The paper on your table will not move unless you move them or something externally moves them. It's not like the paper gets up and moves on its own, even though we do suspect that, yeah. Tons of things on our table apparently, just gets legs and starts moving. All right, usually because of wind or somebody not doing what they're supposed to do, or wonderful thieves. Have tons of thieves around. All right, so that's really good, y'all. Something will not want to change its motion unless you make it change. Now, some changes are very obvious, other changes are not. Okay, so let's continue reading from the handout. This law is a statement of a body's inertia. Inertia is described as an object's inherent laziness or its inability to change its motion. So let's read that again. Inertia is a statement of Newton's first laws. It tells us about an object's inherent laziness, meaning it does not want to change its motion. So if something is sitting down on the ground, it wants to remain on the ground. If something is moving, it wants to continue moving, right? Anybody of you all ever try to run really fast and then stop right on a dime? Will you stop right on a dime or will you fall over? You fall over. You don't ever see, or those sprinters when they've done their 100 meters in 9.3 seconds, 4 seconds, and they stop immediately. No, you're going to rip the muscles in your legs. What you have to do, things that are moving, do not want to stop moving. If you are running or you're walking, you don't necessarily want to stop immediately. You'll have to slow down to stop. Same thing if you had to pick up something heavy. Which time is it the hardest to do? To pick it up or to walk with it?
Pick it up.
To pick it up. If you had to pick up, your school, especially a school bag, that school bag is the heaviest the instant you'll have to pick it up. Ever notice that? It's the heaviest when you have to pick it up. But once you've put it on your back, it's not so bad. Did the mass of the bag change? No. Did the weight of the bag change? No. But that first action of picking up something or changing its motion is its inertia. That object does not want to change its motion. The way how the world is made up, your first motion is usually the hardest motion to create and to cause, or to change your motion is hard to do. So inertia, let's see. Inertia is why we need to wear seat belts. Why don't I have a diagram for this? All right. So what happens when we are moving in a car and we're wearing a seatbelt? When you are stationary in a car, you are not moving while in that car. All right. Everybody agrees with that. Now, once the car starts to move, you are now traveling at the same speed as that car. But the instant that car has to move its velocity, all right, let me see if I have a diagram. Just now, you all. All right, so let's look at this. When we are in a car and we were to sit in this car, we will be moving with the same velocity as the car. Now, only while we are in the car do we move with the same velocity. So when the car is at rest, you are also at rest. But once the car is moving forward, right, you are now traveling at the same speed as the car. So once the car has started moving, say, the car is now moving with some velocity, you are also traveling with some velocity. Now the car decides to stop. How does the car stop from moving? Quickly. Anybody? The seat? No. How does the car stop moving?
Oh, accelerate. Accelerate. No.
The brakes must.
Mr. The bricks.
Oh.
Brakes. Right? So that's how a car stops moving quickly. You have brakes. So when it hits the brakes, the car is going to stop moving. Are you hitting brakes on yourself?
When the seatbelt
Yeah,
got
let's
No,
activated,
we jump into a point there. When the car now comes to a rest, right? You are still moving forward with a velocity. So let's think about it. If you all are coming, traveling together at the same speed, let's look at my both hands, right? On the video, right? Both hands are moving. That's one hand be the All right, let one hand be the car and the next hand be the person. Now, when the car stops, the person is going to continue moving forward because nothing stopped the person. This is why they invented brakes, because they realized that the person is still traveling with the same speed as the car or as the vehicle. So they are going to want to fly forward. So they're going to move forward as if there was nothing holding them back. So let's just think, they're flying forward and there's nothing holding them back. This is how you end up flying into the seat in front of you, and more horribly, either the steering wheel or the dashboard or hitting the window or through the window, because 50 kilometers an hour is plenty, right? We can actually work out how much force you all will fly out of the seat, little lower down, we're going to do that. So without the seatbelt, because we have no brakes to stop us, the brakes stop the wheels of the car, so the car stops. But you continue moving because you were traveling at the same speed as the car. So what happened? What did they come up with? They came up with the idea to invent a seatbelt to stop you from moving forward with the original speed that you had. So it slows you down from hitting the front of your whatever is in front of you. All right, so seatbelts is not just something there that they invent by law, it is physics. All right, it came as a result of physics. All right, now they did take some planning and some design for seatbelts. The very first seatbelt, they thought, you know, since the person is sitting down, right, with their heads back here and whatnot, and the most vulnerable part of your body is your head and your chest. They said, you know what, we could just put the seatbelt, right here. Anybody could tell me what will happen if you had your seatbelt like right around your shoulders or by your head?
you would choke.
You would choke. Imagine if this seatbelt, and you all know the seatbelt, the edge of your seatbelt is thin and sharp-ish.
Yeah.
We had some horrible demonstrations of crash test dummies getting decapitated because of that original seatbelt design. So it took a while for them to realize that the 3-point seatbelt, now it is a 3-point seatbelt. Why? Because we have our shoulder, we have the belt on one side of our hip, and then it comes across and clips on the other side of our hip. So that's called a 3-point harness. And they realized the 3-point harness was the easiest harness to get in and out of and secure a person. It's only later on when they realized that people were driving like maniacs that they needed something more than just a seatbelt. These where they came up with the idea for airbags and then crumple zones. But we're going to look at crumple zones a little later on. All right, that's why cars mash up using Trinidad language. Now, that's why cars mash up during crashes, because the crashes are meant to take all the energy of the impact and put it on the car rather than the person. Yes, it's really stressful to see a car get mashed up, but I think we rather that happen than the people get seriously damaged, because they used to have that long ago. Long ago, the cars were made of nice, good, solid steel, nice, good, solid aluminum, really hard to scratch and dent and whatever. But they realized that the people inside of the cars suffered really terribly during impacts because they got the full brunt of it. All right, think about if somebody were to hit you, right, really hard. You're going to feel that hit really hard. Now, I would have done this in class had I hit somebody, whoever wanted to. But if you were to put a piece of sponge or something in front of where you got hit, that sponge is going to take the impact. If you put like a cardboard box in front of you before you get hit, right, that cardboard box will take all the impact, crumple up, and you would feel just a little bump. All right, now there are some accidents that no set of seatbelts will save you. No crash bag, airbags will save you because you're traveling too fast and too fast. And I think half of the road deaths we've seen this year were a result of people not wearing seatbelts. So people, this is a reason why we wear seatbelt. It's not just is a law. It is there to secure you because physics works. The instant you stop a vehicle, you are still traveling at the same speed as that vehicle. All right, and then you need something to slow you down. Now, if the car is not traveling too fast, you could just put your hand out and stop. That's enough to stop you out. But it doesn't take much. Once you're traveling over 40K, over 50 kilometers an hour, that is enough force on your body where you cannot physically control it. So please, people, wear seatbelts. They do save lives. They honestly do. And I rather get whiplash where I just have to wear that stupid collar for a couple of weeks than have my head crash into the steering wheel or have my head completely shatter and, really graphic things into the dashboard or fly through the window. Less of two evils. So this is going to be in an assignment. I'm going to give you all an assignment on explain how inertia works and explain how friction works, right, as an interaction of molecules. So let's continue reading. Friction is a retardant force. Retardant force means to pull back something. It slows you down. Without friction, things will continue moving forward. But some things cannot move without friction. We need friction to move some objects. So friction is a retardant force, and it is a result of interaction of surfaces and molecules. So you're going to get some homework on friction. I'm going to have you read up some topics, going to have you read up some examples, so then we could explain it together, in the next session. So you're going to get some homework on this. It's just to read up, write up, and I can say I hope submit, but just to read it up because it's going to be for your own benefit. So continuing momentum. Let's get rid of this. Momentum is the forward motion of an object due to an action of its mass. Unlike weight, objects can be propelled forward owing to their momentum. Now, mass is a scalar quantity, and momentum is therefore unaffected by the presence of gravity. So how do we work out momentum? Momentum, if you want in plain, simple English, momentum is the forward motion of an object. Simply, that's what momentum is. It's what carries an object forward. And how do we work out momentum? Momentum is a product of mass and velocity. The symbol for momentum is common P. So P is equal to mass by velocity, whatever the mass of the object is by its velocity. We're not looking at acceleration as yet. So momentum is simply what carries something forward. So this is what people ask, but if something is in space, why does it continue moving if it has no gravity and has no friction? How does it continue moving? Because of momentum. Once an object has reached the space or reached somewhere, it's going to continue moving forward because that mass is pushing it forward. So this is what keeps objects moving. It is your momentum. Law of conservation of momentum. Oh, let's just do the units. Units of momentum. You should always learn your units. Momentum is equal to mass by velocity. What is the units of mass? Use SI unit, kilograms. What is the moment? What is the units of velocity? It's going to be meters per second. So you are going to get kilograms, meters per second. So that is the unit of momentum. Please, your units are extremely important. You get 1 mark for it in your questions. Almost all your labs, 2 marks, at least 2 marks out of the 10 go towards units. All right, so conservation of linear momentum. You all have to learn the law of conservation of linear momentum. So what does it state? The law of conservation of linear momentum states that in the absence of external forces, the total momentum of a system is constant. Linear means to move in a straight line. So we're going to look at how the momentum of an object varies while moving in a straight line. Why do we look at straight line? Because these are all vector components. We look at how something moves between point A to point B while traveling in a straight line. So reading this again, the law of conservation of linear momentum states that in the absence of external forces, we're not going to have things speeding up other objects. We're not going to have things unnecessarily slowing down other objects. The total momentum of a system is constant. So this means total. What is total? How do you all work out total of anything?
By adding.
We are adding. You see this thing here? Lots of students neglect to note, total means to add. So you're going to have to add some values sometimes. So the momentum of a system, continue reading from the handout. The momentum of a system is the same before and after an event. The events that we look at in this topic will be things like collisions, explosions. Explosions could be firing of projectiles. Right, something like firing a cannon, firing a bullet from a rifle, firing a pebble from your slingshot. Those are firing of projectiles. Or exploding. Explosions are when you take one object and you burst it into 2 or 3 parts and they travel at a very high speed. So something to remember, the momentum before an event, this is where we have 2 objects probably sitting on a table. We have 2 objects traveling towards each other. That's your before event. And then after event is when things start moving in different directions. So when performing these calculations, we must first take into consideration sign convention. Now, sign convention is something where everybody in physics did decide that we are going to take into consideration certain directions. Now, when an object is traveling from right to left, we take its velocity as negative. This is just to work out the maths because, again, this is a vector quantity. This is a vector topic, and we have to take directions into consideration. So anytime an object is moving from right, starting from the right and moving to the left, the velocity is negative. And anytime an object is starting from the right and moving towards the left, no, starting from the left, and moving towards the right, your velocity will be positive. So this is what they've done across all physics textbooks across the planet. Doesn't matter what language you're reading, you're writing, you're doing, even in special North Korea where they've come up with their own rules and history and specialness. They have all agreed, the physics will have all agreed that any object moving from left to right has a positive velocity for these calculations, and anything moving from right to left will be negative. An easy way for you all to remember, what direction do we write across the page? Which direction do we start on your page and do we write across the page normally?
Left to right.
Left to right. That's the easiest way to remember how an object moves. And what is the positive one? Just remember, yeah, I start on the left-hand side of the page and I move to the right-hand side. Now that doesn't work for all cultures. If you're doing Arabic, Arabic starts from right to left. If you're doing Chinese, from up to down, right? So, but for us in English and those who came up from Latin derived languages, from left to right is positive. So when we're doing calculations of linear momentum, these are the steps we take, right? Always the steps that we take. 1, you always assign velocity signs. 2, we calculate the total momentum before an event. 3, we derive an expression for the total momentum after the event, and then we solve. So let's look at an example. Let's get our next color pen. I have an example here. I have a 5-kilogram object traveling to the right at 10 meters per second, and it is traveling and going to intercept an 8-kilogram object that is traveling 5 meters per second to the left. So what's going to happen? Those two objects are going to come hit each other. Sorry, they're going to come hit each other, and then they're going to bounce off. We all know that, right? Or one could hit each other and one could stop moving and one could continue moving. We're going to do questions like that. So after they have now come hit each other, they're going to either bounce back or continue moving at a certain speed. So after the event, the 5-kilogram object reversed its direction and is now moving 4 meters per second to the left, while the 8-kilogram object is still moving to the left at some velocity. So we want to determine how fast is it moving while going in this direction. So let's look at the rules. Let's look at the steps to take when you're doing these questions. The very first thing you do is to put signs for your velocity. So we're going to put plus and minus signs for our velocities. The 10 meters per second, it is going from left to right. So is that positive or negative velocity?
Positive.
Positive. The 8-kilogram object is going from right to left. So is that positive or negative?
Negative.
Negative, good. And then I have the 4 meters per second. Is this moving negative or positive?
Negative.
Negative, good. All right, and we do not know, let us assume that the V here is also negative because they said it's moving in that direction. So we have done step 1 where we put our plus and negative signs. Step 2, we're going to work out our total momentum before your event. Your total momentum means that you find the momentum of each object. How do you find momentum? Remember, momentum is mass by velocity. So let's look at our first object here. First object, mass by velocity. It's going to be 5 by 10 plus, what is our second object here going to be? All right, that's your second object. So you're going to get plus 8 by minus 5. Everybody okay with that? You get your momentum of each object, which is mass by your velocity. Mass by your velocity. So let's work this out and see what we get. 5 by 10 is 50. 50 plus 8 by minus 5 is minus 40. So 50 plus and a minus is minus. So 50 minus 40 is 10. Everybody understood what I just did?
Yeah.
Yeah, miss.
Right? We take the total momentum. Total means to add something to something else. So that is step 2, which is to so step 1 was to do your plus and negative signs. Step 2 was to work out your total momentum before. Step 3, let's read, we derive an expression for the total momentum after. So let's look at our total momentum after. Let's get all these funky colors in here. It's going to be the momentum of the 5-kilogram object added to the momentum of your 8-kilogram object. So let's do our momentum. Remember, momentum is mass by velocity. So it's going to be 5 by minus 4 plus 8 by minus V. Let's simplify this to see what you'll get. We're going to get 5 by minus 4 is minus 20. 8 by minus v is minus 8v. Now this is an expression because we cannot simplify this anymore. If v cannot be added or subtracted from a number, so we can't say, well, 20 minus 8 is 12. No, it has this v. We do not know the value of v. So what we do, we leave the expression, and this was what they did say, that we derive an expression. An expression is a number and letter that cannot be simplified. And step 4, we just equal the 2. So I'm going to have minus 20. You always write down before is equal to your after. What was your before? 10. What was your after? Minus 8v minus 20, same thing. And I'm now going to solve for v. So you carry your numbers across. So you're going to have 8v is equal, minus 20 jumps the equal sign, becomes positive. 20 plus 10 is 30. So v will be, how do you get rid of the number in front of a letter? We divide by that number, including the sign. So you're going to get 30 over minus 8. And here you're going to get 3.75 meters per second. And the negative number here indicated that it is in fact traveling from right to left. All right, this is all in the handout that you all had to download. So you're going to go through it. The class is nearly over. All right, so we first take, let me just hit you all here with the colors if you want to take a screenshot. All right, you all can take screenshots too when you're working out stuff, when you're doing your class recording. All right, so you work out your total momentum before your event. Then you work out your total momentum expression after your event. You equate them, and it's going to be a very simple algebraic solution, algebraic equation to solve, and you find your value. So what we can do, class is going to finish here just now. We can try question 2. All right, I'm just going to put up the answer in the group for question 2. All right, so you all can go and try question 2 probably at the end of the day, or if you all have a free period afterwards, give it a try, see if you can get it. But the best way you all can do this, do a diagram. You see how simple and nice this diagram is? Just draw a little ball to represent your first mass, a little ball to represent your second, and you put your arrows to indicate your directions. So start you all up quicker. For example 2, let's just get some working space. A 5 kilogram object, a 5 kilogram object is traveling to the right at 10 meters per second. It collides with an 8 kilogram object that was traveling to the left at 5 meters per second. So this is your before. All right, after the collision, so if you look at the after diagram, the 5 kilogram object rebounds. Rebounds mean to bounce back, as we've just done that in a lab. So the 5 kilogram object is now going to rebound and move at 4 meters per second, while the 8 kilogram object travels in the same direction, and we want to work out its velocity. So you have the diagram there. You go through your steps. 1, you put in your plus or your minuses, put in your plus or your minuses, work out your total momentum before, work out your total momentum afterwards, equate them and solve. So I'm going to put the answer just now in the chat so you all can see whether or not you went wrong, and we'll just go through the working afterwards. So I'm going to stop share screen there. All right, if you want to write it down quickly, write it down quickly because class is basically done. All right, just draw your stuff really quickly, or you can remember it because you do have the handout. So I'm going to stop the recording, and we'll do this the next